Machine learning is fundamentally oriented toward prediction rather than explanation. The goal is to identify models that produce accurate predictions on new, unseen data, rather than to interpret coefficients or test hypotheses as in traditional statistical inference. In the test training approach of machine learning, data are divided into a training set for model estimation and a test set for evaluating predictive performance. A key insight is that a model with better in-sample fit, that is, with a higher multiple R-squared, does not necessarily yield better predictions. Instead, metrics like mean squared prediction error, or MSPE, provide a more appropriate criterion for model comparison. To understand why simpler models can sometimes outperform more complex ones in prediction, we need to understand the bias-variance trade-off. Bias reflects systematic error, that is, how far predictions are from true values on average, while variance reflects instability, that is, how much predictions fluctuate across samples. Complex models tend to have low bias but high variance, often overfitting noise in the training data, whereas simpler models have higher bias but lower variance, potentially underfitting true patterns. The optimal predictive model balances these two sources of error. Building on this framework, machine learning techniques can be understood as tools for navigating the bias-variance trade-off. Methods such as ridge and lasso regression introduce penalties to shrink coefficients, increasing bias but reducing variance, while more flexible approaches like splines, regression trees, and deep learning decrease bias at the cost of higher variance. It is important to note that increasing model complexity introduces a tension between predictive accuracy and interpretability, especially in methods like deep learning, where internal representations become opaque.